Hello guys, nice to meet you again. In today's video, we are going to learn about data compression and the Huffman algorithm. So our main aim here is to understand the concept of data compression. Yes, so if they ask you what data compression is, what does it mean? Yes, so we are going to look at that, and then we are going to look at the Huffman algorithm. Yes, we are going to delve into it. So without wasting much time, let's see. So data compression is the process of reducing the size of a file or data set by eliminating redundant information, allowing for efficient storage and faster transmission. So yes, that is what data compression is. So when you look at the diagram you have there, the original data, that is from the sender. Now it is encoded, and then this encoding makes it look smaller. So, and then it is transmitted, but before the user receives it, it is decoded. So it goes back to the original data. Yes, so this is more like multiplexing and then demultiplexing. So you multiplex when you are sending, and then you demultiplex when you are receiving. Okay, so let's look at this diagram here too. So we have data compression methods. Now we have two main types. We have the lossless method and then the lossy method. Now the lossless method is more for text and then program. Then the lossy is for images, videos, audios, and so on. Now what this lossless means is when it is being transmitted or when it is compressed, right, it doesn't reduce its quality. For example, text, when you compress text, it's still same as text. Yes, so we are going to talk more about the Huffman. So those are the three types we have there, as you can see. Now the lossy, we have images, videos, and then audios. So whenever you compress these, the quality reduces. Think of it like you sending a picture to someone on WhatsApp. When you send it, you realize that the quality reduces before it gets to the person, or when it gets to the person. Yes, so we have these three main types. We have the JPEG, which is images. We have the MPEG, videos, and then the MP3, which is music. So someone may ask, why do we need to compress data, right? Why do we need to compress data? So one, there are so many reasons why we need to compress data. So one is storage saving. So when you compress it, it saves storage, that is, it reduces the size. And then two, we have for faster transmission. So whenever the data is smaller, it is transmitted faster. Yes. And then we have reduced cost. So if it is smaller, then it uses how do you call it, smaller resources to transmit it, therefore the cost is reduced. Yes, so these are some of the reasons why we need to compress data. Now we have a question here. Using the Huffman algorithm, solve the percentage save space of the string enemy attack. Enemy attack. So they've given us a string, we can see. So with the Huffman algorithm, the first thing you need to do is that you write the words, and then you express them in increasing frequencies. So those that have frequencies appearing more than once, you group them as once. So it's like you are going to arrange them in priority. Yes, so the ones come first, and then those that are having frequencies of 2 and 3s. Yes, so when you look at the enemy attack, E is 2 in there, and then A is 2 in there, and then T is also 2 in there. So let's write the ones which occurred only once. So we have N, M, Y, and then the space. We have the space, and then we have the E appeared twice, and then the A also appeared twice, and T appeared twice. So let's indicate the frequencies there. So the N appeared once, Y appeared once, the space appeared once, the E appeared twice. So as you can see from there, E, N, E. So E appeared twice. So the frequency of E is going to be 2. I think we missed something. The CK. Yes, C appeared once and K also appeared once. So let's write that. We have the space and then the CK before the E, and then the A, which also appeared twice, and then the T, which also appeared twice. Alright, so this is what we have. So the frequencies N is 1, M is 1, Y is 1, space is 1, C is 1, K is 1, E appeared twice, which is 2, A appeared twice, which is 2, and then T also appeared twice, which is 2. So the frequency of E, A, T is 2, 2, 2. So that is the priority I'm talking about. You arrange them in increasing frequencies. Okay, so the next thing that we do is, let me copy this and then paste it on the next page. Okay, this was giving me hard time. I think we've been able to do that. Now let's drag it to the top so we have enough space below to do this. Okay, so I think 1 didn't, 2 didn't show. So we have the N, M. Let's write that M and then the Y. Okay, so I think we are good to go. So let's check the total number, right? The N is 1, M is 1, Y is 1. So we are going to add the least frequencies. So N, M, we add them, Y and space we add them, and then the C and K we add them. Now the ones with the frequencies of 2, we just write them down. So E is 2, and then A is 2, T is also 2. Now let's add the smallest again. So we have 2, 2, which is 4. We have 2, 2 again, which is 4, and then we have 2, 2 again, which is 4. Now let's add the two frequencies. So we have 4 and 4, giving us 8, and then the 8 and then the last 4 there, we sum them also. So we add the 2, 8, and then the 4 there. So we realize that when we after we are done drawing the tree, right, we are going to get 12, which is the 8 plus the 4. Why is it 12? Now let's refer to the question that was given, or the number of words that we had. We had N, which is 1, M is 1, Y is 1, space is 1, right? And then we also have the C and K. So these are summing up to 5. Then the 2, 2, 2, so 6. So the 2, 2, 2 gives 8 plus 2, which is 10, plus 2, which is 12. So in total it is 12. So this tells us that our tree that we've drawn or sketched there is correct. Yes. So whenever you draw the tree, compare the number that you had as a final answer to the number of strings or words that are there. Okay, so let's move on. So we are going to invert the table, right? We are going to turn the table upside down. So if you don't want this to confuse you, you can just do it on a sheet of paper, and then when you finish, there's no need for you to rewrite it again. You can just turn the paper upside down, and then you are going to get the how it is going to be presented. Yes, so the next step is that we invert the tree. So let's do the inversion. So let's redraw it, but an inverted form. So we are turning the tree upside down. So in turning it, we have 12, which is the last number. You have 4 and then 8. So the 8 and then the 4. And then what sums to give this 4? We have 2 and 2. 2 and 2. And then the 8 is 4 and 4. So let's do that. The 4 there was 2 and 2. We've done that. The 8 is 4 and 4. So let's do that. So I think we made a mistake. The 8 is supposed to be at the left hand side, and then the 4 is supposed to be at the right hand side. So that is what you get when you invert it. So let's do that. I think I missed that. So we have 12. So let's write the 12. So the 8 will be at the left hand side. So 8 at the left hand side. And then 4 at the right hand side. Alright, so what sums to give this 4? So from what we have there, or from the tree, we realize that to get the 4, right, we have 2 and 2. So 2 plus 2 give us the 4. Now let's come to the 8. How did we get the 8? We summed the 4 and the 4 there. So the 8 is the sum of 4 and 4. So let's go back and then refer to that. So we have 4 and 4. Okay, now what sums to give this 4? What sums to give this 4? Now we have 2 and 2. So 2 plus 2 give us 4. So let's go back and then secure that. 2 and 2. Okay, now let's go to the next 4. The next 4 there, we had the summation of 2 and 2 again to give us that 4 there. So let's do that. Okay, let's finish up with the 2. So we have 1 and 1. The other 2 there is also 1 and 1. So the 4 is 2 and 2. Let's go back and then secure that. 2 and 2. So whenever you are doing this, you need to take your time, because if you do a mistake, it's going to affect your final answer. So the 2 there was 1 and 1, give us the 2, which is the N and then the M. And then the other 2 there, the frequencies appeared twice. So the E and A and then the T. So write it EAT. The frequencies appear twice. Now we are assigning the numbers or the letters to their frequencies. So we have N, M, Y, and then the other one there was the space, and then the other one there again was the C and then the K. So when you go back to the tree that we did, we realize that N is 1, M is 1, Y is 1, space is 1, C is 1, K is 1, and then the EAT, the frequencies appeared twice. So let's circle these ones. The space is 1, the C is 1, K is 1, and then the 2's that we have there is the EAT. So this is our tree. So this confirms that our tree is correct. Okay, so now that we have the tree, what do we do next? Okay, so the next thing is that we draw a table, right? We draw a table, and then how do you call it? First of all, we number all the left hand side of the tree to be 0, or the right hand side of the tree to be 1. So every right hand side takes 1, 1, 1. So 1, 1, 1. Every right hand side. So you do that. Every right hand side you make it 1. Every left hand side of the tree you make it 0. So, and then when doing this, it can be a bit confusing, so you need to take your time to do that. So I repeat, all the left hand side goes to 0, so every left hand side of the tree is 0, and then every right hand side of the tree is 1. So that is how we are going to derive or generate the Huffman code. So now that we've labeled this, the next thing is that we draw our table with the code and then the character. So we have the character. I don't have my pen here, so I'm having a little difficulty with the writing, but I think we are good. We are good. So that is it. We have the character and then the code. So you are drawing a table. So the table is divided, and underline it to make it look like a table. Okay, so I think we have this. Yes, but it doesn't look so nice. It doesn't look so nice. So this is what we do. Let's clean this code. Let's clean this table. Let's clean it, and then use an actual table. Yes, I actually wanted to write this, but I think the space there is enough. This is enough. So EAT, having difficulties. So let's just erase it. Let's just erase it. So yeah. Okay, is it good? Let's see if we can maintain this. If we can't, then we should just switch to actual table and then put in that. It will be a bit difficult, but I think I would try and then do that to make the work look nice, because underlining it with the small interface makes it look some way. So let's erase them. Let's erase everything and then use an actual table. Let's erase them. Wipe. Okay, so I think we are good. Let's insert a table. So we have 2 by the number of letters, which is 12, plus the heading. So we are going to use about 13 how do you call it, columns. So let's focus on the first one. So we have the character and we have the code. Okay, so our first character we had there was the N. So let's write that. N. I think auto capitalization is on, so it capitalizes automatically. Don't worry about that. So we have the Y, the space, the C, the K. So let's add more tables to it. As I said, we are going to use about 13 columns. Okay, so we are good. There's the C key, K, and E, A, T. Okay, so we are done with the characters. Now let's move to the code. So now that we are done with the characters, let's focus on the code. And this is the most critical part, the most crucial part. So pay attention when doing this. Yes, so in deriving the code, the end there, we are going to trace from the 12 to where the end is. So when we look at the graph or the tree, right, from the 12 it comes to this and it traces down to the 9. So everything there is 0. So we have 0 0 0. So that is the n. The n is 0 0 0. So let's fill the table with the code. So we had n to be 0 0 0 0. Now let's look at the m. The m there, that is where the m is. So in you have to trace the m from the 12 or the mother or the parent to where the n is, the m is. So that is 0 0 0 1. So we have 0 0 0 0 1. So that is the m. So we do this to all the other characters. So for the y, let's try the y too. So the m was 0 0 0 1. Now the y is 0 0. Right, you are looking at the y. So 0 0 1 0. So 0 0 1 0. That is our y. 0 0 1 0. So we write it. Let's fill the table with our y. 0 0 0 1 0. Now let's go to the C. So we are tracing. Okay, the space is there. We have the space. So we are tracing from the parent to the space. So we have 0 0 1 1. So that is the space. 0 0 1 1. Let's fill the table with that data. So we have 0 0 0 1 1. So we are going to do the same to all the other characters till we get to the final one, which is the T. So the C is 0 1 0 0 when you trace it from the tree. The K there is 0 1 0 1. That is the K. The E there, when you trace it, you're going to get 0 1 1. And then the E there, when you trace it, you're going to get 0 0. And then the T there is just 1 1. So the T is 1 1. As you can see from the rightmost, from 12 to where the T is 1 and then 1, because I said that all the right hand side is going to take 1 and all the left hand side of the tree is going to take 0. Yes, so that is it. And then don't forget our frequencies. The EAT appeared twice, so the frequency is 2. So it means that the number of bits that we have, we are going to multiply everything by 2. That is the EAT. So as you can see from there, that is the frequency. They all appear twice. So let's do that. So E is 2. So we are going to look at the ones that have frequencies that appeared more than once. So that is the AAT. So that they all had 2. Alright, so let's put in that. So E was 2, so multiplied by 2. A was 2, also multiplied by 2. And then T was also 2, multiplied by 2. Okay, so now that we have this, when you multiply the 3 bits by 2, you are going to get 6. When you multiply the 2 bits by 2, you are going to get 4. When you multiply the 2 bits again, which is 1 by 2, you are going to get 4. Yes, the E is supposed to be 6, so let's work on that. It is 0 1 1, which is 3 bits by 2. 3 2 is 6, so let's do that. It's 6. Okay, so this is going to give us 4, right? This is also going to give us 4. This is going to give us 4. There are 4 bits. The next one is also 4 bits. The next one is 4 bits. The next one is 4 bits. The next one is 6 bits that we have 4 and then 4. So we are going to sum all these bits, right? So when we sum them, we realize that the sum is supposed to give us something like sum is equal to, we have 4 plus 4 plus 4 plus 4 plus 4 plus 4 plus 6 plus 4 and then 4 again. So that is it. So when we sum everything, we are going to get a sum of 4 plus 4 is 8, plus 4 is 12, plus 4 is 16, plus 4 is 20, plus 6 26, plus 4 30, and then 4, which is 34, and then 4 again, which is 38. So we are going to get the sum to be 38. So now the formula is percentage save space is equal to the original size. So the original data that was given, which was the enemy attack, right, minus the compressed. So what we just compressed, the table that we drew or the Huffman algorithm that we used was the compressed form. So the compressed, so let me just use percentage S is equal to the original. So the original, as you can see, was enemy and then attack and then the space, so it becomes 12 letters, right? So minus the compressed over the original times 100. Now when you are storing 4 bits of when you are storing let me say a word or a letter, right, you are going to use 6 bits. So every letter you save is going to take 6 bits. So that is the ASCII system, the ASCII. So we had 12 letters there, so every letter is 6. Now the 12 by the 6 is going to give us 96, right? Yes, you have a calculator, you can do that. Then yes, so the letters there were 11, the enemy and then the attack were 11 plus the space, which makes it 12. Now the 12 by the ASCII, the ASCII, so every letter there takes 6 bits. So 12 by 6 gives us the 96 minus the compressed. So what is the compressed? It was 38. The sum gave us 38. So minus the compressed, which is 38, over the original, which is 96, times 100%. So when we evaluate this, we are going to get the final answer to be 60.4175 2%. So this is the space that we've saved, right? We've saved, or we've been using the Huffman algorithm. We've been able to save a space of 60.417%. So because it is a lossless data, the original quality of the string doesn't reduce before let's say it is transmitted to the receiver end. So therefore the percentage save space here is, or of the string enemy attack space attack is 60.417%. Yes, so this is our final answer, or you can round it to the nearest decimal place, so you have 60.42%. So this is how you go about the Huffman algorithm and then the data compression in general. So this is the final answer. The final answer is 60.42%. So this is the space that we've been able to save instead of transmitting the actual or the raw data, which would take up a bigger space. So that is it for today. If you have any question, feel free to put that in the comment section. If there is any concept you want us to hit on, feel free to do that, and then we will be glad to help you. Yes, don't forget to smash that subscribe button and then like this video so you get updated whenever a new video is dropped. Yes, so that is it for today. Have a nice day.